them. So first of all, I'd like to thank the organizer for the opportunity to speak and also for putting together this really wonderful workshop and conference. I've been learning a lot and I look forward to many more. Okay, so today I'd like to share with you some interesting connections between conformal manifolds and continuous SymTFTs. And in particular, I'll show that by using techniques and ideas from continuous SymTFTs, we can understand a large class of conformal manifolds. Okay, so the main player, first of all, the reference, so this is based on work 2 up here. And I also would like to point out 2 papers, in particular this paper by Sergei Dubovsky, Stefan Nigro, and then Massimo Perotti, which I draw a lot of inspiration from. And then there's a related paper by Ricardo and friends. Good, so the main player of today's talk will be about conformal field theory. But I want to also make a disclaimer that I would not use any explicit techniques on knowledge about conformal field theories. So the talk will be mostly based on symmetry talks, and everyone should have the background to understand it. Okay, so conformal field theory, in short, are the endpoints of renormalization group flow. So because of this, they have scale invariance, which often enhance into conformal invariance. They are of fundamental importance to condensed matter physics, statistical mechanics, string theory, and holography. And a very important and challenging task is to systematically classify and organize them. So somewhat interestingly, the space of conformal field theories are actually not always discrete. So for example, in some cases, the CFTs can be continuously connected by exactly marginal deformations. And this gives rise to what's called conformal manifolds. So when I talk about exactly marginal deformations, what I mean by that is just adding some exactly marginal operators into the into a Lagrangians, and then add some parameters in front of them. So this is called conformal manifolds because it's naturally endowed with a metric. And this metric is defined by the 2-point functions of the exactly marginal operators. And this is known as the topological metric. So let me also give you some motivation why it's interesting to study this conformal manifolds, other than that it's very interesting mathematically and it's very cool. So one reason comes from condensed matter. So the existence of this conformal manifolds tied with some unconventional critical phenomena in condensed matters. So for example, given the phase diagrams, often the case CFTs are isolated at critical points. But however, in some notable cases, they actually form an extended submanifold. So this happens, for example, in the case of Lagrangian liquid or XXZ chain. And another good reason to study them is related to string theory and hierarchy theories. So in string theory, if we have exactly marginal operators on the worldsheet, they correspond to some massive scalar fields in the target space. So these are often called moduli. And in recent years, there has been a lot, and one thing to emphasize is that because these are massive fields, okay, so they are the most important ingredients that enters into effective actions in target space. So that's why they're very important. And in recent years, there has been a lot of progress activities in the swampland programs, which basically is concerns about constraining the UV completions of quantum gravity, of effective field theories to quantum gravities. So in particular, one conjecture that comes out, that is when we are looking at infinite distance points on moduli space, which often happens when the scalar fields acquire very large expectation values, then it was conjectured that a tower of massless states actually appear. Okay, and this statement, if you translate into a CFT statements, it becomes to what's called a CFT distance conjectures, which concerns about the infinite distance points on conformal manifolds. So since the talk will be mostly about 2 dimensions, or 1+1 dimensions, let me just state the distance conjectures in 1+1 dimensions. So the statement of distance conjecture in 1+1 dimension is that consider a 1+1 CFT at infinite distance points on a conformal manifold. This is characterized by having some primary operators whose scaling dimension vanishes, okay? And this, in fact, has been proven in one direction by Hiroshi and Ifan, and the other direction still remains as a conjecture. Okay, so this is some motivations, at least for me, to study this conformal manifold. And, yeah, please. Yeah, so I mentioned this topological metric, right? So you can, sorry, let me repeat the question. So the question is about what infinite distance means. So the infinite distance is defined with respect to this topological metric I defined before. Does that make sense? Yeah. Yeah. So because this conformal manifolds can be non-compact, so that's why there, if you start with a point, there is some infinite distance point that will take infinite like distance with respect to this.
So there's a reference point, right? So what's special about a reference point?
No, the reference size is not important. It's infinite distance.
Yeah. But infinite distance from some other point, right?
Some points in the bulk, yeah. Any random points in the bulk, yeah.
Okay. Any two other points are finite distance.
Okay. That's right, yeah.
So it doesn't depend on the.
Yeah. That's right. Yeah, yeah. Don't. I'll give you examples later. Yeah. Don't. Yeah. Good. So let me continue. So today I'd like to ask the following questions. Given that there's this interesting conformal manifolds, are there any structures underlying them? In particular, this is a symmetry conference. So the question I would like to ask is that can symmetry help us understand them? Okay. And so let me give you the punchline before diving into details. So the punchline is the following. So I'm going to show that given any 1 plus 1 DCFT with more than one U1 currents, then there exists exactly marginal operators that can generate a conformal manifold. And in fact, this covers a large class of conformal manifolds in 1 plus 1 dimensions. And the existence of this conformal manifolds, in fact, has nothing to do with the CFTs. It can be purely understood from the symmetry point of view by showing that, by noticing that, or proving that any two CFTs on such conformal manifolds are in fact related by topological gauging. Okay? And this topological gauging can be understood as some zero-form symmetry in the corresponding continuous SymTFTs. And along the way, I'll also discuss some implications about the global form of the symmetries. And then we'll review interesting connections between the topology of the conformal manifolds and anomaly. Good. So let me start by telling you a class of conformal manifolds generated by what's called current deformations. So we're in 1 plus 1 dimensions. So every conserved current in 1 plus 1 dimensions has conformal dimensions equals to 1. So that means that by taking two such conserved currents and compose them, then we can define a marginal operator. And in particular, I would like to look at this very specific combinations where the currents index are contracted by epsilon tensors. So in general, this is an operator that is marginal at zero deformations, but it might not remain marginal after finite deformations. There are some non-trivial conditions that enters into the marginality, exact marginality. So one sufficient conditions for exact marginalities, which I'm going to prove later, is that if this currents J1 and J2 generates two commuting U1 Lie algebra, okay? I want to emphasize that I'm labeling the currents by Lie algebra, not by the global form of the symmetries. So in particular, the global form of symmetries could be U1 or R, but at this point, I will not make any specific commitment about global form. And I'm going to come back to this later in the coming slides. And one counterexample of this is simply consider SU2 Lie algebra, and then there are two U1s generated by sigma x and sigma y, and then they don't commute. And this fell the exact marginality condition. Good. So let me give you some examples just to give you like some ideas of how this conformal manifolds look like. So to start with, let's consider unitary compact CFTs. Okay. So in any unitary compact CFTs, a conserved currents always decompose into chiral and anti-chiral currents. So that means that this current deformations is nothing but the JJ bar deformations, which has been discussed in the 80s. Okay. And in fact, the exact marginality of the JJ bar deformations was proven in these papers using chiral algebras. But in this talk, I will not assume the chiral algebra. I'll just assume the U1 times U1 symmetries. And then I'll give you more examples later. So what are the examples? So the first natural examples come from Narayan CFTs of compact bosons. And this is basically generalizations of Lagrangian liquid. So the conformal manifold of this Narayan CFTs are parameterized by symmetric matrix GAB, which corresponds to metric in the target space, and then the anti-symmetric matrix BAB, which corresponds to B field in the target space. And then both this deformations can be generated by current deformations, building up of the momentum currents and the winding currents. We can also discuss deformation of WZW models, for example, which has been discussed in these papers. So this is what happens in the case of unitary compact CFTs. But now I want to move on the territory of non-compact CFTs. So in fact, in non-compact CFTs, currents do not always decompose into chiral currents. And this is where current deformations bifurcates from JJ bar deformations. So a simplest example is just consider a non-compact complex scalars given by phi. And then let's just talk about a symmetry that rotates this compact scalars, okay? So this is the corresponding currents. And one can show that this current cannot be a conformal primary, cannot be a descendant, in fact, this is not even a well-defined operators. If you will look at the state operator correspondence, this operator is not even normalizable. But despite the fact that these currents are not well-defined in CFTs, we can still use them for current deformations to generate conformal invariant nonlinear sigma models. So an example is given by, let's say we take R4 sigma models. Basically, the target space is just R4. So it can be parameterized by two complex scalars. And then so we have two complex scalars, so we have two U1 symmetry that rotates them. So using that two currents, we can build up a current deformations. After the final result, it becomes something like this. Don't worry about the details, but I just want to show you how this looks like. But just one comment I want to make is that if you think about this, every CFT should correspond to some kind of, on the worksheet, correspond to some solutions in the target space Einstein equations. So it turns out that the metric, if you extract the metric and B fields from these expressions, they are related to the flat space data by what's called TST transformations, which was first pointed out by Looney and Matessina. So what is this TST transformations? It's basically saying that if you start with a solution of Einstein equations, you can generate new solutions by applying what's called TST transformations. Okay, good. So now let me discuss. I gave you examples of both compact CFTs and non-compact CFTs, and we see that current deformations are not the same as JJ bar deformations in general. So in all examples I've shown so far have explicit actions. So we can write down differential equations for the actions, find the currents, and then solve the flow equations. But I want to uplift the discussion to more high levels. In particular, that requires us to define or formulate current deformations abstractly without actions. Okay. So how will we do it? How can we do this? So the way to do this is to first notice that currents in general can vary along the flow. So if you're at the middle of the flow, you don't know what current you're actually referring to. So to account for that, what we need to do is that we need to track not just the actions, but then the generalization of actions, which is the actions that couples to the background gauge fields. So then in the middle of the flow, we can extract the currents by taking derivative respect to the gauge fields. Okay? So now the flow equations can be formulated by the following equations. So the variation of the actions is basically given by the same expressions, but now except that the currents can be extracted along the flow. Okay? And then this can be translated into equations for the partition functions. Yes?
Maybe it's a very small. Maybe it's a small question. But do you set A to 0 after you take the derivative or not?
No. So
can you elaborate on that?
Yeah. So I required to keep track of this assay along the flow. But then at the end,
but usually we would define the current by taking the derivative with respect to the connection and then turning off the background after taking the derivative.
That's correct. But then what I want, so that's what happens if I talk about how S with A turnoff transforms. But then I want to keep track of the whole families, how it transforms, so that I can extract the currents at every point. So this is the flow equations that I demanded to satisfy. So it's stronger than this equation. Okay. Good. Yeah. Okay. So maybe this J can depend on A. Yeah. This J can depend on A.
It doesn't.
Yeah. Yeah, that's right. Yeah, I wouldn't say improvement, but it can have some explicit depends on A. Yeah.
Sorry, quick question. The starting point is always a free theory?
No.
Okay.
Yeah, I mentioned WZW models. It's not
okay.
Yeah.
Sorry.
Okay. Good. So we can uplift it into equations for partition functions. Okay. So good. So this is the equation we like to solve. In fact, it has a very simple solutions, which was pointed out by these papers. So the solution is given by a kernel representations. So the way to understand the solution is very simple. So we start with the partition functions with deformation parameter taken to be 0, and then then we integrate this partition function against the kernel. Okay. So here B is something we integrate against, which is supposed to be a gauge fields that couples to the original partition functions, and this kernel is given by this form. So there's an important comment I want to make is that even though A as the background gauge field has the gauge symmetries, this B, where it's supposed to be sitting at the place where a gauge field is supposed to be sitting at, is actually not a gauge field. It is R-valued one-form field without gauge symmetry. Because if we look at the kernel, it explicitly breaks the gauge symmetry. So that's the reason. Okay. So, and the fact that this is an R value one-form symmetry does not depend on the global form of the symmetry. And this is important later. Good. So now I have this kernel representations. So, so if I now set the background gauge fields A to be 0, then this is the expression that I have. So given these expressions where B is not, is just a one-form field, we can actually restore the gauge symmetry of B by introducing a R values Stocker field, and then decompose this little b into big B, which is R gauge fields, and then the Stocker d phi. Phi is given by the real Stocker field. And then there's a R valued gauge symmetries that acts on B and phi. Good. So we can always just use the gauge symmetry to just fix phi to be 0, then we just recover the same expression as before. But notice that the seed theory, the theory that we start with, could have a Toph anomaly. Okay? So that means that the partition function may not be invariant under gauge transformations, and in general, it can take a form like this. So now assembling this piece, and then to substitute little b equals to big B plus d phi here, the expression that we get is basically this. Okay? So now we can recast the original kernel representations into a path integral over R valued gauge fields and the R valued Stocker field. But now notice that what's nice about this expression is that we can integrate out phi. If we integrate out phi, what it means is that it's set dB to be flat, to be 0. So we are basically summing over flat connections over R gauge fields. Okay? And because this is we're just summing over flat connections, so this is actually a topological manipulations. So what we're doing here is topologically gauging a R times R symmetry with a continuous torsion. Okay? And a continuous torsion is parameterized by lambda. And because this is a topological manipulations, it therefore preserves conformal symmetries as well as central charge. Okay? Good. So this gave a one-line explanations why current deformations is exactly marginals. Good. So now I would like to come back to the issues of global aspects, the global form of the symmetries. So in our discussion so far, I have made no commitment about a specific global form of the symmetries. But since there's very little to say about R symmetries, I will just focus on the case where all the symmetries are all taken to be U1. So in this case, this is the kernel representations. But one thing I want to emphasize is that even though the symmetry that the theory has is U1 times U1 symmetry, what the kernel representation is doing is effectively gauging, implementing a topological gauging by treating this U1 times U1 symmetry as an R times R symmetry. Okay? And this is in fact very important because as a U1 times U1 symmetry, there could be a Toph anomalies. But if we treat it, if we only consider flat R gauge fields, then the U1 times U1 anomalies can be trivialized. Okay? This is why we can gauge this R times R symmetries. So using this kernel representations, I'm going to, and also with this additional input that these symmetries are U1 times U1 symmetries, I'm going to show that at rational points, this topological gauging in fact can be localized. It can be localized into discrete gauging. And the details of this discrete gauging actually depends on the anomalies. And using these relations, I'm going to review the interesting connections between topology of the conformal manifolds and anomaly. Okay, so let's start with the simplest case when there's no anomaly. We are just consider the case when it's anomaly free. So in this case, I set a deformation parameter already to be 2 pi times n divided by n, where m and n are co-prime. Okay, so I'm already looking at some rational point on a conformal manifold. So in this case, first we notice that for anomaly-free U1 times U1 symmetry, the partition function is invariant under shifting this gauge field B by an integer gauge fields, so 2 pi times integer gauge fields. Okay. In fact, this shift corresponds to performing a large U1 gauge transformations. So now because this part, oh yeah, Clay, you have questions?
Sorry, can I just ask? So I thought the 2-point function of the currents was the anomaly, and so isn't the 2-point function always non-zero?
2-point function of the current, yeah, that has condensed data of anomaly. Are you asking about?
I'm asking about the anomaly-free assumption and sort of how is it related to, what assumption are you putting on the 2-point function? Maybe just expand on that.
Oh, I'm just saying that the U1 symmetry is anomaly-free. Basically, what I'm saying here, if you want to translate into Cosmoley algebra, then it just means the level is 0. You're not happy with that?
You don't restrict to unitary. Okay.
Unitary, okay. Yeah. Sorry, Shuhan has a question. So.
Okay, I think I have an answer to Clay's question. So here, the U1 is not assumed to be chiral. So it has a holomorphic component and an anti-holomorphic component. And the anomaly-free condition is that K equals K bar.
Oh, okay. Yeah. Oh, yeah. Thanks, Shuhan. Yeah. That's right, yeah. I'm just assuming they are vanilla U1 currents. We have U1 symmetry, we have U1 currents. That's it. Yeah, there's no left and right there. Yeah, that's right. Yeah. I think in 2D CFT we're too used to assuming chiral currents. And so yeah, I'm assuming less, and then there's something more we can do. I think that's the point. Good. So anyway, in this case, anomaly free just means the partition function is invariant. Yeah.
Is the current bona fide field in the field theory or not?
I mean, I showed this example where it doesn't need to be a field in the field theory.
But then, are you allowed to add it to the Lagrangian?
I can still do current deformations. Yeah, the two things that.
But you said that the operator is not well defined.
Yeah, it has, but the whole procedure that I did still goes through. Maybe it's not well defined in the sense of it's not gauge invariant. It's gauge invariant, but it has infinite norm. Yeah, it's not normalizable. That's what I'm saying.
Yeah, but then you're not allowed to add it to the Lagrangian.
I wouldn't say that. Yeah, I think it's something we can still do.
2D Landau-Ginsburg model, we add x to the p to the even though it's not a good operator.
Yeah.
Run there and come back.
Yeah. Brennan has a comment. Brennan should repeat his comment. Yeah.
My comment was just that in a 2D Landau-Ginsburg model, just a non-compact scalar field, we add x to the p to the action, and x is not a good operator, so it's sort of, we do this often.
We should stop this. Yeah,
let's stop there.
Yeah, we'll come back to that. Yeah.
Let's continue this.
Yeah. At least this procedure that I described goes through. Okay, that this topological gauging goes through. Yeah. Good. So let me now come back to So when there's no anomalies, when it's anomaly free, it just means the partition function is invariant under the shift. So then, if you have rational points, we can imagine doing first summing over B1, which are 2 pi times integer gauge flows. Okay. So those 2 pi times integer gauge flows doesn't enter into this because of this anomaly free conditions. So I just need to sum over them here. So the consequence is that they could localize B2 to be 2 by m divided by n times some integer gauge flows. So next I can sum over n2, which is little n times integers. Okay. So again, these things will not enter into partition functions. So what it does is just localizes B1 now to be 2 pi times integer gauge flows divided by little n. So when that's settled, what happens is that the things that we start with, which is R times R gaugings, actually just a continuous sum of flat R connections, just localizes into a sum of Zn gauge flows. Okay, and then in particular, these expressions can be understood as gauging a Zn times Zn subgroup of the U1 times U1 symmetry with a discrete torsion, and this is the discrete torsions which inherited from the continuous torsion. Okay, so one immediate consequence of this is that now we can just take the case little n to be 1. So if we take little n to be 1, we are setting lambda to be 2 pi times n. But in that case, we are gauging a Z1 times Z1 subgroup, which means that we are gauging nothing. Okay, so that means that the deformed theory is actually identical to the original theory we have. So this means that in fact, what this deformation is doing is tracing out a closed cycle on a conformal manifold. So anomaly free implies it's going through a closed cycles on conformal manifolds. And a simple example is given by the B fields of Narayan CFT, C equals to 2 Narayan CFT. So let's consider doing a current deformations of 2 copy of compact bosons using the winding currents. What it does is to generate the B field term. So this is basically a term that's similar to theta terms in gauge theories. And the coefficient lambda is 2 pi periodic, and this is consistent with what I said before. Good, so this is what happens when it's anomaly free. What happens when it's anomalous? So for simplicity, I'll just assume the case with mixed anomaly, okay? So this, I assume that how the partitioning function will transform. This is what the partitioning function will transform. So in this case, one thing to notice is that the equation of motion of phi is actually influenced by the anomalies, which is parameterized by this k. And this k turns out to take the form 0 minus 1 over 2 pi, 0 and 0, okay? And then now the equation of motion of phi actually does not always impose the flatness conditions, except at 3 points, when lambda equals to plus or minus infinity and lambda equals to 2 pi. And the physical meaning of these 3 special points will soon be clear. But as long as we are staying away from these 3 points, the kernel representations implements a topological gauging. So now let's we start with these expressions, and then we focus on the rational points on the conformal manifolds. So because of anomaly, this partition function will not be invariant under the large gauge transformations. So if we perform shift big B by 2 pi times integer gauge fields, it has an extra phase coming out, okay? So now we can just play the same game as before. Let's first sum over B1, which is 2 pi times integers. This restrict B2 to be this forms. Next, we sum over N2, which is n times integers. But now it restricts B1 to be 2 pi times the integer gauge fields divided by n minus n. And this additional minus n is coming from this anomaly contributions. So when that settles, this is what we have. We are localizing a continuous integral of flat R gauge fields into a discrete sum of integer gauge fields, where one of them is a Zn gauge fields, the other is the Zn n minus m gauge fields. And the way to interpret it is gauging the non-anomalous Zn minus m times Zn subgroup of the U1 times U1 symmetry without discrete torsion. So let me emphasize that U1 times U1 symmetry has anomaly, but the Zn minus m and Zn subgroup is actually anomaly free because n minus m and n are co-prime. And because they are co-prime, there are also no discrete torsion to turn on. So the way to interpret this expressions is that this is not discrete torsion. This is needed to trivialize anomaly. Okay? So here we have seen that, let me now again discuss the consequences of these expressions. So let me now go back to the special points at lambda equals to plus and minus infinity and 2 pi. So the claim is that the special points are actually the infinite distant points on the conformal manifolds. Okay? And the way to argue that is following. So let's consider lambda equals to 2 pi. So in that case, we can approach this by taking n to be n minus 1, and then we take n to be infinity. Okay? So what it's doing is basically just gauging a Zn subgroup, because this is just Z1, so we're not doing anything. We're just gauging a Zn subgroup in the U1 times U1 symmetry. So when we gauge a Zn subgroup, we'll need to introduce twisted sector operators. And the twist, when I talk about twist here, I mean the labels for the topological defect lines that attach to twisted sector operators are given by 2 pi times integer divided by little n. Can I get a few more minutes? Or? Yeah, okay, good. So then now when I take n to be larger and larger, I'm taking finer and finer, finer and finer twist. So because the dimension of the twisted sector operator is supposed to be some smooth functions, at least around 0. So then when we take n to be infinite, then there must exist some operators whose dimension actually becomes smaller and smaller as we take n to be larger and larger. So then all we need is to use the nice results by Hiroshi and Ifan. It just tells us that lambda equals to 2 pi must be at infinite distance on a conformal manifold. So similar arguments go through for lambda equals to plus and minus infinity, except that we need to pick some other way to approach them. Okay? So what we have seen here is that anomaly tells us, is tied with the non-compactness of the compact bosons, while anomaly-free gives us compact directions. And indeed, this happens in the case of the radius for C equals to 1 compact boson CFTs generated by current deformations within the momentum and winding currents. And in this case, if we do this deformations, the radius is jumped from r to 2 pi r divided by 2 pi minus lambda. And indeed, lambda equals to plus and minus infinity is at infinite distance. Oh. Is it like a force? Oh. I see. Okay. Maybe it's telling me I should stop my talk. Yeah.
Let's watch which button they press this time.
should I?
Button on the back.
Okay.
Yeah, back of this, but I don't know.
Maybe we shouldn't do it. Yeah, let's be safe. Yeah. Okay. But anyway, I can say something like so. Yeah, yeah. Just topology is typed with anomalies. Yeah. Yes. Can you try? Okay. Something happened. Oh, okay. Okay, let me go here. Okay. So, okay, let me just, yeah, I think I don't have much. I should just wrap out. And let me just say.
Take a couple minutes.
Yeah. But I think it doesn't like my connect. Okay. I'll just do it here. Okay, good. Yeah. Okay, so let me now just comment on continuous SymTFTs, how everything can be understood from continuous SymTFTs. So I'll skip the continuous SymTFT intro. Yeah, okay, I'll wrap up now, yeah. So one thing to emphasize is that changing the topological boundaries amounts to implementing a topological gauging, okay? So now let's consider a continuous SymTFT for multiple U1 or R symmetries. It's basically given by BF plus Chern-Simons theories. And then there's a Chern-Simons terms which is capturing the anomalies. So here, this B is always an R gauge field, while A is a U1 or R gauge field. It depends on whether we are talking about U1 symmetry or R symmetry. So I'll skip this, but then the important thing is that there's dirichlet boundary conditions, and dirichlet boundary conditions is implemented or realized by adding these terms to the boundaries. And then if we look at equation of motions, naturally it will enforce as A equals to 0, okay? And then on these boundaries, the conserved operators are basically given by integral of B. So this suggests that this B should be viewed as a conserved current. So this will be important because now let's consider a SymTFT with two copies of either U1 or R symmetries. It will has a zero form symmetry generated by a topological surface, which is given by B1 wedge B2 integral, and then there's a lambda that appears here. And in particular, when we consider U1 times U1 symmetry without anomalies, this B1 and B2 have integral holonomies, so lambda is 2 pi periodic. So that means that this is a symmetry, a U1 symmetry, and this will reproduces the statement I made before. So now, if we have this surface operator, we can push it to topological boundaries. So what it does is it modifies the boundary conditions by current deformations, because B1 and B2 are basically currents, right? So if I add that to the boundaries, this is performing a current deformations. If I integral B1 and B2, this is what I get. This is a kernel that appeared before. If I push it to dynamical boundaries, it actually generates a -1 form symmetry. So -1 form symmetry just means that there's parameters in my theories. And this -1 form symmetry is a U1 symmetry if we're considering U1 times U1 SymTFTs without anomalies. So this reproduces a statement that I made before that we are going through a cycles on the conformal manifold. Good. So let me just conclude. So one key takeaway of today's talk is that we should embrace this topological gaugings of continuous symmetries, and continuous SymTFT could be useful for something. And in particular, using this topological and continuous SymTFTs, we have a good handles over conformal manifolds coming from at least current deformations. So things I didn't have time to discuss includes, for example, applications to boundaries and defects, higher dimensional generalizations. And then, of course, there are many interesting directions to generalize. So let me stop here. Thanks, everyone. Yeah.
Very quick question. Can you come back a couple of slides?
Yes.
On the operator U that you wrote?
Yeah.
Yep. Yeah. This operator off shell is not gauge invariant. Is that a problem?
This operator is off shell.
Yeah.
Off shell. Yeah. So I'm talking about its on shell. Yeah. When I write this operator, the correct way to define it is using condensation defect.
Huh?
You can write it as condensation.
Okay.
That's the correct way to define it.
But can you write a similar expression, like without talking about condensation defect, an expression like this that makes it gauge invariant of shell?
I think
Because sometimes it's possible, but I don't know about this case.
Yeah. I think you can add some Stoker field to make it like true on shell, and then that equation of motion is coming from Stoker fields are trivial. Yeah, just is consistent with the bulk equation of motion. So, Nadi has a question. Sorry, I think. Yes.
Sorry, is your bulk, is it gapless or not?
It's gapped. It's gapped.
It's gapped. And
Yeah.
B, what are the conditions on the gauge fields in the bulk?
Yeah, so B are real gauge fields and A are U1 OR gauge fields. It has infinite, if you put it on like torus or something like that, it have infinite ground states. Infinite number of ground states, or infinite partition function, but it's still gapped.
Is B, so what are the fields in the bulk?
So B and A. B is the R gauge fields, A can be U1 OR. Depends on your group.
And you think it's gapped?
It's gapped, yeah, it's gapped, yeah. I mean, this theory is, it has infinite degeneracy, but it's gapped. Yeah. And in fact, it's also robust in the sense that what's go between vacuums are line operators.
Okay, so B is an R gauge field, right?
B is R gauge field.
And in one of the formulas you had B with a lambda out front.
That's right. Mm-hmm.
But lambda, so why is lambda periodic?
Oh, because, okay, so let me go back here. So when there's no anomalies, then you can sum over the flux sector of A, okay? So then that will constrain B to be actually having integral holonomy. Even though B is a real gauge fields, after equation of motion is integral holonomy. So then now it comes back to here, then this means that this thing has integral. This integration is actually integer. So that's why lambda is 2 pi periodic.
I see. Thank you.
Yeah. Thanks. Ifan has a question.
Do you have maybe intrinsic definition of distance from properties of gauging? And if you do, then maybe there's a way to try to prove the inverse of the statement that infinite distance also implies vanishing gap.
That's a very good question. So I actually don't have a good answer at this moment. There should be one way to, yeah, you're talking about distance, right? Yeah, there should be one way to parameterize the distance using lambdas, I think so. Yeah, I think there should be a way, but I haven't worked it out. Yeah.
Okay.
Yeah. That's right. Sahan has a question or something.
Is all of your examples of infinite gauging correspond to picking some finite subgroups? So take a limit of finite subgroups and in some limiting. For example, in the U1 times U1 anomaly, you could approximate some alpha with some rational numbers. So, and you get ZP times ZQ, where P and Q are co-prime and P over Q limits to some irrational number.
Yeah, so, I think that's right. Because I said at rational points, it's discrete gauging. So,
right, but in those examples of U1, irrational points are the limits of finite gauging. So is it true that in all of your examples are all gauging correspond to limits of finite gauging?
Yeah, so let's talk about compact boson. In that case, if you have irrational points, it corresponds to gauging a Z and then a U1. So Z and U1.
But it's true that it's also a limit of finite gauging, right?
Yeah, that's right. Yeah.
So I'm saying, is it true that in all of the examples, these gauging correspond to limits of finite gauging?
Yes. Because I said at rational points, they are discrete gauging.
I see.
Of course, at irrational points, you should.
But then the follow-up question that if, for example, you could also ask if you have SU2, if you could gauge SU2 in a flat gauging it.
Yeah, you can do that. There are papers that work on this. I can tell about it later. Yeah.
But it's not a limit of finite gauging, or can you understand it as a limit?
You cannot take a that's not a limit of a subgroup of SU2. Yeah. That's right. Thanks. That's good. Right?
Okay, if there are no other questions, let's thank our talk.
Yeah. Thank you.